All right. So here in this types of rocket propulsion, we will first of all see that what are the classifications of rocket propulsion. Okay, so here we have so many types. Okay, chemical, chemical, nuclear, and the electrodynamic. So in under electrodynamic, we'll be having all those kind of electrostatic, electro thermal, and also on electromagnetic will be there. Now under chemical, this liquid, solid, hybrid, and in nuclear we have the fission and fusion, and electrodynamic will be having you have another three types: the electrostatic, electrothermal, and electromagnetic. Okay, so static, electrothermal, and electromagnetic. Okay, so basically it has been classified in these are the basic types. Now we will focus on the first on the chemical. So here the word chemical represent that means that propellant that is a fuel that is used, that will be something will be having some kind of chemical reactions. Okay, now under this chemical we have another three types. So we will see what are those types. First we will give more focus on the liquid rocket and solid motors, rocket motors. So always when we use this word liquid rocket engine, and here solid rocket motors. Okay, so when we discuss about liquid rocket engine, there are lot many propellants. The liquid propellants are used. The most common one is a monopropellant and bipropellant. Okay, so what this liquid rocket engine does is that the main substance or the working substance is a fluid, okay, which will undergo some kind of you can say chemical changes and thermodynamical thermodynamical changes. Okay, so which combines of oxidizer and a fuel, right? So most of the oxidizer we have seen last class that liquid oxygen, it can be of nitric acid, right? And when we consider the fuel, that may be of some kind of liquid hydrogen and so on. So there are of various forms, various forms of liquid rocket engine. Now when we talk about that, before understanding going into the what are the propellants, we will see what are the basic component. So when we consider the basic component of this liquid combustion chamber uh, uh, rocket engine, the main component becomes the combustion chamber. Okay, so combustion chamber consists of the injector, okay, injector, then followed with the combustion chamber, then the convergence section, throat, then the divergence section. Okay, now the nozzle part of this any thrust chamber, either it can be fixed or it can be of thrust vector. It can have some kind of secondary thrust, that means it can have some mechanism or actuators that we can deflect the direction of the nozzle. So accordingly we can make the pitching, yawing, and rolling movement of the aircraft. Okay, so just like how during the space how they do the, apart from the fins and the aerodynamical bodies, using the nozzle they can also perform the pitch, yaw, and rolling. So these are the basic thing. The pitch, you know how this pitching movement occurs. It helps to create a nose up and down, right? Yaw means it will be like sideways direction, right? Sideways direction. If there's a nose, right? If this is a nose of that rocket, it will create in sidewise direction. Okay, rolling means it will roll the axis, along the axis it will be rolling, right? So all those things can be done by the thrust vectoring. Okay, so they will be also, we'll be seeing what are the types of thrust vectoring. I will just give you the glance. Now coming to an propellant. So here in this gate they ask the what are the different types of propellant. You should have the idea about the propellants, the name of the propellants, that is very important, or sometimes the combination of the propellants. Okay, and the characteristics of the propellant, that is very very important. So here we have lot many different types of propellant. Just a second. Okay, so first comes a bipropellant. The name, the word bi represents the two separate liquid propellants. Okay, one will be need to have the oxidizer, another one was a fuel, and this is one of the most commonly used one. Okay, so bipropellant. Now there are lot many bipropellants are there. Okay, the best one was a liquid oxygen and the RP1. Okay, that we call as a kerosene sometimes. Okay, then liquid oxygen and hydrogen, this is another bipropellant combination. Then another bipropellant combination is a liquid fluorine and liquid hydrogen. All those are the bipropellant combination. Okay, where we have the oxidizer and the fuel, right? So the case where we don't need any kind of oxidizer, it is a self it itself have contains some kind of oxygen to produce a combustion, right? So that kind of propellant is called as a monopropellant. Now very important is an hypergolic bipropellant combination. This, the term represents hypergolic means it has an ability to combust by itself. So that means without any igniter it can ignite. That means when both the oxidizer and the fuel come in contact with each other, it will get ignite. So that kind of propellant is called as a hypergolic bipropellant. Did you got my point? Just unmute. Okay, fine. Right. So you in gate question, what they will do is they will give you the couple of options. Okay, so you have to find out the which among the propellant combinations belong to that particular domain. Okay, so you have to remember the name. Maybe either they can give in short form or in an expanded form. Okay, either of the way you have to be very careful with that. Okay, you have to remember each and every name. Okay, so let's first see what are the common hypergolic combinations. Okay, the first combination is an aerosine and the nitrogen trioxide. Okay, nitrogen trioxide is also can be represented as a NTO. Okay, N, this is nitrogen, T, right? So either you have to remember the short form, you have to remember the both actually. Okay, so then next combination is an UDMH. Sometimes they will just write UDMH, and you have to find out what is that, whether it is an bipropellant or the monopropellant or something. Okay, so UDMH is unsymmetrical dimethyl hydrogen. Okay, unsymmetrical dimethyl hydrogen. Okay, so this is another combination with the nitrogen trioxide, NTO. Then next we have the, this is the fuel actually, right? This is a then they can also ask like which one is a fuel and which one is a oxidizer. Okay, so this is the fuel. Unsymmetrical dimethyl hydrogen is the fuel and nitrogen trioxide is an oxidizer. So please do note down the names, that is very very important. Okay. Next comes the monomethyl hydrogen, MMH. Okay, MMH, monomethyl hydrogen. So this is done. Then we have another one is called as a tonka. Okay, tonka, one of the question they have just asked what is a tonka represents and also on. Okay, so tonka is another type of hypergolic bipropellant. Okay, next comes another T-tip. T-tip, right? So what is T-tip? T-tip is a triethyl bromine or the triethyl aluminum. Okay, I hope you are noting down the names. These are the very very important. Okay, have you noted down? Okay, sometimes they can also give you in this way, like they will give you the chemical formula. Okay, so please do note down the chemical formula also. Okay, this is a nitrogen trioxide represents N2O4. Okay, N2O4. And just give me a second. Hydrogen was not here. Monomethyl, this one, monomethyl hydrogen represents CH3NHNH2. Okay, this one represents monomethyl hydrogen, CH3NHNH2. Okay, and unsymmetrical dimethyl hydrogen represents, okay, so CH3 2 NNH2. Okay, this is an unsymmetrical dimethyl hydrogen. Right, have you noted down? Yes, like not all. The main thing is this, both this MMH and UDH are soluble. The main good thing about them is these are the soluble hydrocarbons. Okay, but whereas if you use hydrogen, which is not, and all the hydrogens are toxic, but MAH is of course there will be an toxic at some point, but if I compare the toxicity among this both monomethyl, unsymmetrical and monomethyl, this is more toxic. This one is more toxic as compared with this. Okay, yeah, so this one is more toxic to inhale, right? This one, but here in case of this UDMH is not that as toxic as compared to this. Okay, so these are these are actually like see, obviously this since they are having some kind of ammonia, right, component, they will be slightly toxic only, but it is only depends on how much like quantity it will be, it will be toxic, right? Okay, just a second. Yeah, yeah. Triethyl boron and see, because it is boron, it will be slightly less. Aluminium, yeah. Because we don't have anything hydrogen. Whenever there is a hydrogen, it will be like kind of toxic in nature, right? Not as toxic as compared to this two. Yes. Arosine, I'm not sure with arosine and how much it is toxic and right. Let me find out that. Okay, because it had been used long back actually. Arosine, yeah, okay, arosine is also see 50 percentage hydrogen, so obviously this will also contain. Yes, yes, yes. Hmm. Okay, right, fine. Now you must know what are the list of monopropellants. Okay, this is very important. The list of monopropellants, you see, first is a hydrogen peroxide. Okay, hydrogen, nitromethane, methyl acetane. Okay, these are the monopropellants. So you must remember the what are the different types of monopropellants. Okay, so please note it down, the monopropellants. Okay, so right, another name is there. Another monopropellant name is there. It's called as a hydroxyl ammonium nitrate. Okay, hydroxyl ammonium nitrate. So this is also belongs to an monopropellant group, and among this all, this particular, or in short they call as a HAN. Okay, HAN, HAN. So among all those things, it contains of very rich in oxygen. Okay, this contain very rich in oxygen, right? You got the point? Shall I skip to next? Okay, so I hope you have noted down all the points, right? Next comes non-hypergolic. Okay, non-hypergolic is like which needs an energy to start the combustion. Okay, so the particular engine needs an igniter, right? So such kind of propellants will have the called as a hypergolic. Monopropellant we have discussed, that coal gas propellant is there, then cryogenic propellant, storable propellant, space storable propellant, gel propellant. Okay, there are lot many types, but those are the very important one which we have discussed. Then another one is important is a cryogenic propellant. So you can understand that what is the temperature of a liquid oxygen and the liquid hydrogen. Okay, this liquid oxygen is an oxidizer and liquid hydrogen is a fuel. Okay, right, now already we have discussed this before. Okay, now this is very important, that how yeah, one more important point before coming to this gelled propellant. Okay, there are some kind of gelled propellant which are the thexotropic fluid, okay, or liquid. What is mean by thexotropic liquid? What is mean by thexotropic liquid? Anyone? Very good. It is a non-Newtonian fluid, which already we have seen. So, which is a non-Newtonian fluid dependent with the time, right? So, we call as an another name is there for this. Like what happens? What happens in this thioxotropic fluid? It is a non-Newtonian fluid. What is that represent? Non-Newtonian fluid. It is dependent with the time. The viscosity dependent with some time, right? So why we are not using that much? Because it is because the storage is a very big issue. Okay, so longer period of time, if you store, that property of that propellant might change. Okay, just an example of the thixotropic liquid is a paint. Okay, so once you open the lid of the paint, right, and after using for a while, and if you close it, and if you don't use for a longer period, you will have some thick layer, right? So due to that's a periodical change, it will change its property, right? The fluid property will change. So that is a very good example of the thixotropic liquid or the fluid. Okay, and this gel propellant is one among them, right? Okay, gel propellant will be having like it will be very flexible, right? It will be in a, first of all, it will be in gel in nature. In this gel propellant you can combine various what we called dusted materials, right? You can use various dusted materials, and yes, yes. No, doesn't leak. I'm not sure about that. Doesn't leak or something. But we cannot say doesn't leak. If there is a liquid, there will be chances of leaking. We cannot say it will not leak. Okay, but gel jelly in nature will be very what we say, like this is another different type. Actually at present this gel propellant this is going on, research is going on, and the another important of gel is to make an effective heat transfer in this gel propellant. What happens, they as we have said last class, like we they used to do regenerative cooling, right? So in that regenerative cooling jackets, they give this gel coating, and that they spray some amount of aluminum particles. Okay, some ratios are there, they spray. So in that, it provides a very effective cooling system to that jacket, but it cannot be used for a very huge engine. But yes, for the smaller engine, for the maybe of 1 ton or maybe 0.5 ton of thrust chambers, they can use this gel propellant, and it has been tested also. Okay, got it? Okay, and another important thing, um, important thing is there won't be any kind of separate igniters are required for this gel propellant. No plug injectors are required. That is another good thing. Okay, the sorry, just give, no, just a second. Sorry, yeah, sorry, I just missed, somebody said something. Yeah. So the first characteristic was like it doesn't require any separate like plugging of injectors. Okay, like controlling will be much easy in the gel propellant, especially as compared with all other. this controlling will be much easier, but we cannot use for the big and it doesn't produce a huge specific impulse actually. Okay. And then next disadvantage is like it the storage is a very major issue in this particular gel propellant, because it changes its property. Okay. So that becomes one of the disadvantages, right? Okay. I hope you have noted down the points. Okay. Am I audible right now? No? Am I audible right? Okay, fine. So next comes the how the feed mechanisms are done. Okay. So we have the two basic types. One is a gas pressure feed system that you can see over here. Okay, that you can see over here, and this one is an turbo pump feed system. Okay. So basically what happens in an, this is the gas pressure feed system. So they will have a separate oxidizer and fuel tank. Okay. And from the neck position of the tank, okay, so from the neck position of the tank, what will happen, it is connected to an high pressure gas. So what will happen, always there will be tendency to flow from high pressure to the low pressure, right? If this is pressurized, it is moving over here, and it will gradually, when this valve will be opening, it will move along this side, right? So using the check valve, so once it open, it will come out over here. There will be a your igniters, sorry, injectors. So in the injectors, it will be feeding, lot many different types of injectors are there. So based on the different type, the type of the cylinder, that injector will be used. So again, they will have the combustion, it will expel out. But in case of turbo pump, this is the turbo pump feed system. Okay. So in case of turbo pump feed system, what we have is the propellant from the tanks are pumped into the combustion chamber, okay, which is driven by this particular gas turbine. Okay, they will be having a separate gas turbine which will be completely driven by that, and the turbines works under, the turbine works under just a second, can you see my slide? No, just a second. Ended. Just a second. Now can you see it? Okay. So what happens, this turbine works under a very high pressure, okay, high pressure and temperature, where it will be generating from the main combustor. So then what will happen, then it will flow, it will speed up this rotate this pump. From the pump, it will drag it from both from the fuel tank and oxidizer tank, and it will bring out to over here, and valve will open and it will expand. Okay. Now to understand this, as I've said, you have to understand one more fact is a thrust vector control. Okay, thrust vector control in liquid propellant. Okay, so how we control our pitching moment, rolling moment, and yawing moment. Okay, so first one we have is an gimbal or hinged. Okay, So here what will happen, there will be along this axis, it will be hinged. Okay, there will be some kind of hinge mechanism. Okay, so that particular, so based on the hinge, it can, if this is the particular axis of the thrust chamber, you can move. If you move along this angle, your thrust chamber will also move likewise. Okay, so when the thrust chamber move along this side you will be getting your force or the thrust, so the aircraft will move along this particular direction. So based on the direction where we need that all the movements, pitching movement, yaw movement and rolling movement, so accordingly you have to move your hinge, like how the aircraft's other control surfaces are deflected, like ailerons, elevators, radars. Similarly, using this thrust vector control in a liquid propellant, okay, this is one of the mechanism called gimbal or hinge mechanism. We can just twist the thrust chamber based on our required direction and we can produce the thrust on that particular direction. Okay, next is a jet vanes. Jet vanes. Now what happens in the jet vanes is like they'll be having kind of let me erase this part. Here in the jet vanes what happens, there will be one kind of vein, like which will be like almost like a wing shaped structure will be suspended at the I can say end of this nozzle. Okay, so but here it won't be moving, the thrust chamber will be fixed, but here a wing like structure, or I can say the airfoil like structure, which will be having some rotating mechanism which can deflect. So when the jet comes, it will deviate accordingly, right? So can you understand the difference? Here the thrust chamber will be fixed, but they will have some suspended wing like structure which will be moving based on the required direction, and this particular wing like structures, right, or you can say the fin like structures will be usually made of very high temperature material like titanium alloys, high carbon steel and so on. Clear? Is it clear? Sorry. Yes, moreover like a stabilizers. Okay, stabilizer based on the required thing, it will be done. Okay, then third one is we have the secondary injection. Okay, so what is that secondary injection means? Like we have the main thrust chamber, right? This is the main thrust chamber. Here there will be some kind of additional channel from where the additional fluent will be coming over here, right? So where the amount of fluent is more, so that particular side the thrust will be more, right, which is expelling out, and where we don't have, where the thrust will be less. So likewise there is another method of balancing or controlling the movements of the rocket. Okay, this is another method. Or another is there, they keep another small rockets. Okay, another small rockets, another way is there. So what they do, they have a separate tank over here. So which direction they want more thrust, they eject the fluid over there, right? Other side they will keep it off. Got it? So this is another is an secondary ejection. Okay, they have the, this is a main, right? This is a main thrust chamber. They will be having another secondary one, which will be ejecting out. The fluid, another fluid will be ejecting out. Okay, right? Got it? Okay, so these are the basic types. Okay, so mostly the gimbal mechanism are used. Even the gimbals are also used in like if you see the back of the rocket, right, you'll be having like this. Have you ever seen that? Yeah, this same thing can be used in solid propellant also. Exactly, right? So if this is a main thing, these are the 1, 2, 3, 4. You have 4 nozzles. Okay, this I'm the showing from the back end, right? This is a thing I'm showing from the back end. Now if I am activating this 1 and 2, right? If I'm having 4 nozzle, I'm activating 1 and 2. Now what will happen to the rocket? Which force will it act? Which motion it will form? It will form yaw, roll or pitching. It will activate a pitching, right? Pitch up, right? Now if I'm activating 3 and 4, it will be the pitch down, right? You got the point? Okay, next. Okay, just imagine 1, 2, right? Now I am making 1 and 3 activating. I am activating 1 and 3. Which side, or what will be the motion of the rocket? Which side it will move? It will form an yaw movement. It will move towards this way, right? Because this side thrust is there and other side thrust is not there, right? Now similar way we will have the rolling motion also. Okay, how? If this one is active, yes, diagonally, exactly, right? So on that time the aircraft will roll along this way. If this one is active and this one is active, it will roll on this way, right? Clear? These are the basic motions of an rocket, right? So there are a lot many additives are there, the properties of additives. So these are theoretical one, so please go through that thing, then why it is selected, how it is preferred to select the liquid propellant and so on. Just have a look. Yes, now there's another important thing, the injectors. Okay, so you know what is the function of the injectors? Can you anybody tell me what is the function of the injectors? What are the functions of yes, it sprays into the chamber, which make a proper balancing of mixer ratio of an of a fuel and the oxidizer, right? Okay, so there are lot many different types. Okay, so basically it consists of 5 types. Okay, 1, 2, 3, 4 and 5. Okay, the 5 types. So double impeachment stream pattern, from that you can understand very clearly. We will be having an alternative fuel manifold and oxidizer manifold, fuel manifold and oxidizer manifold. So what will happen? So each manifold will be having 2 jets. So from the jets they will be spraying, they will be one plug will one plug of the fuel and one plug of the oxidizer will be spraying together. Okay, so when this one fuel and one oxidizer is spraying together with a proper mixture ratio. Okay, mixture ratio, this is very important, mixture ratio. With proper mixture ratio, then it is, that particular thing is called as a double impinging stream pattern. Then try triplet impinging stream pattern. When we say that, when we have that two oxidizers or the and one fuel, so all those things are combined together and they are spraying. So such kind of pattern is called as a triplet impinging stream pattern. Okay, so obviously you know the amount of oxygen should be more as compared with fuel, right? Then we have self impinging stream pattern, right? It will be like creating itself. By the name itself it says that self itself it will spray. So here we have again alternative of fuel oxidizer, fuel oxidizer. Okay, so they have the two jets, the both the jets will be will be spraying by itself. It is not combining the combining into the oxidizer and fuel. So these are the mostly types. These first and two types are mostly used in a hypergolic propellants. So you know hypergolic propellants, when this oxidizer and fuel come in contact with each other, it will start to combust. We don't need of any kind of igniters. But in case of self-impinge stream pattern, we need our igniters to make a separate combustion process. Okay, same as a shower head type. Shower head type is represent like we have again alternative fuel oxidizer channel, and they are not impinging itself. At some point we have the jet points, so fuel comes out from the jet points and like how it combustion process takes place. Okay, so for this kind of, especially for the shower head stream pattern, we need a very long combustion chamber. Okay, we require a very long combustion chamber, because when it will spray, right, we get some space that when this oxidizer and the fuel will become in contact and the combustion process will proceed, right? So this is one of the very disadvantage for an shower head stream pattern. Okay, so okay, now comes to the last one, is a hollow post and sleeve element. Okay, or it is also known as an coaxial injectors. Okay, this is also known as a coaxial injectors. Mostly nowadays we use this coaxial injector, though its design is very complicated, okay, very complex in nature. So but still it shows it has been proven advantageous when the as in the point of combustion. Okay, so most of the cases we use an axial injectors. Okay, so in that what happened, inside there is one first main tube, right? Inside the main tube we have another small main tube, which is not completely till the main tube over here the point where the spraying occurs, right? So here the liquid oxygen comes, and outside the channel we have the preheated why here it is gaseous oxygen, because as I've said yesterday or the previous day, that when we are using a reheating system or regenerative cooling system for an liquid propellant, when it is coming inside the injector, it changes its phase from liquid, it transforms into the gaseous form, right? Because it is absorbing all the heat, it is transforming from the liquid to the gaseous form. So that's why they have used the term called as a gaseous hydrogen. So gaseous hydrogen, the preheated gaseous hydrogen, that is a fuel, comes from the outer channel and the liquid oxygen. So both they get, there is some space they call as a resist. Okay, that resist they get mixed together, and together it gets sprays out from the ejector nozzle. Okay, so that helps and very better and efficient way of combustion, and that is the coaxial injector. Okay, gaseous hydrogen. Why? Because in the previous class, if this is an our axis of our rocket, okay, this is a thrust chamber, throat, and this is the nozzle. Okay, now what happens in case of regenerative cooling system? Okay, so regenerative cooling means they will be having an outer jacket. Okay, there will be a jacket. From here they will feed a liquid hydrogen. Okay, they will feed whatever the fuel may be. It will be in the form of liquid, right? Liquid propellant, right? So when it comes, it will be flowing from the outer jacket. Because of the high amount of heat produced in the nozzle, so it will transform its liquid form to the gaseous form. So that preheated gaseous form will come and feed into the injector, right? So that's why it is written as a gaseous hydrogen. Clear? Okay, fine. So now comes to the solid propellant. Okay, so liquid propellant is clear to all of you. These are slightly theoretical one, so you have to read. I'm just giving the main you can say main layout. Okay, so in when we talk about liquid propellant rocket, so we call as a liquid rocket motors, we don't call engine. Okay, now in this propellant yeah, in this particular liquid propellant motors, just remember the maximum thrust or it can be generated using solid propellant is 2 Newton to 4 million Newton. Okay, so whatever the combination or the size, so thrust of an solid propellant can be range from 2 Newton to 4 million Newton. So here also you can use actuators. Okay, just give me a second. Sorry. So here also they use some kind of actuators. Okay, actuators to control the it is like actuators for the thrust vectoring control or the direction control. Okay, the if I want to compare with a liquid rocket engine with a solid rocket, the solid rocket will be having the much simple and easy and require very little in servicing. Okay, these are the qualities of the solid propellant rocket motors. Okay, first of all, why if I'm telling it's very simple, because in case of liquid propellant we had that lot many systems to provide oxidizers, to provide separate cylinder to carry the fuel, then pressurizing, then feeding, right? It is very complex. Then next, once we have the complex things or so many systems, then you will have servicing will be, maintaining will be high, right? You have to take care. But in case of the solid rocket motors, we don't need any kind of separate tankers like oxidizer or the propellant, oxidizer or the fuel, right? We will have a solid propellant which will just like an incense stick, right? All of you have seen incense stick, agarbatti, all of you know. Yeah, it is moreover like an that. Okay, that is one of, you can consider the agarbatti is an solid propellant. Okay, so how it happens, like if it is agarbatti, right? If it is agarbatti and you have ignited over here, right? You have ignited over here, so what will happen, gradually it will burn, right? Gradually it will start to burn. But in case of solid motors, what happen, we keep the igniter at the center part. we keep the igniter at the center part. So if I want to look from the cross section of that particular propellant, okay, solid propellant, so it will be something. If I'm keeping the igniter over here, right, so it will be started to burn along circumferential ways, right? It will start to burn in a circumferential ways. So that to burn out and to produce that thrust, it shows much easier as compared with the your rocket propellant. And here the cooling system, if I talk about the cooling system, there are a lot many cooling systems are used. First of all, they use a ceramic liners, that then thermal coatings they use. The materials they use high temperature materials, and film coolings are used. So that kind of cooling system are used for an solid propellant rocket motors. Now these are the basic things that you must understand, the components for an solid propellant rocket motors. Okay, so you can see this is the propellant. Where is the propellant? Okay, you can see here is a igniter. Here we need mandatorily we need to use a igniter. Okay, mandatorily we need to use a igniter. Okay, then this is the outer casing. Liner, you know what is the function of the liners, right? Can anybody say what is the function of the liner? What is the function of a liner? Anybody? Anyone? Very good. It will protect the case from heating. It is moreover like an kind of thermal coating. Okay, so basically we can say any rocket solid rocket components have a basic thing. One is a motor case. Okay, one we have the motor case, then we have the nozzle or exhaust gas, and then third one will be the igniters. Okay, so motor case will be basically will be designed based on the various configurations. Okay, the first, please note down these points. The motor design will be based on the propellant grain configuration. Now what is mean by propellant grain configuration? So you can see this cross section. Now with what kind of shape it will be, right? Whether it will be star like, whether it will be like this, or it will be like this, right? So first the motor casing will be depends on that what kind of propellant grain configuration it will be. Next is how much amount of load and pressure value will be impinged. Okay, or I can say loads and pressure. Okay, how much amount of load and pressure will be impinged in this particular motor case. Then next comes internal heating. How much tentative heating will be there? What are the aerodynamic heatings? What are the thermal stress, strain, right? And the fourth one is cooling system based on proper material selection. Okay, so these are the things to construct or to design. We need to take care of this this motor case, right? First, the type of propellant grain configuration, the amount of load and the pressure will be acting on this particular chamber. Then what will be the possibly internal heating, aerodynamic heating, the thermal stresses and strain, right? Then cooling system, how we can make an effective cooling system based on proper material selection. Clear? Have you noted? Okay, now talking about what are the material used for an motor case fabrication. While making this fabrication, or what kind of possible materials are used. First of all, they first choose a high strength material. Okay, please note down these points. They used a high strength material. Second, they use wounded filaments, reinforced plastic. So you can expect a small question, which one among this will be suitable for fabricating this solid rocket motors. Okay, so such kind of questions you can get, so you should know what are the possible things are used. Then third one is the combination of metal case with wound filament. Okay, so first is a high strength materials, wounded filament, reinforced plastic, then the combination of both. Right? Now, so this is motor case is done. Then comes nozzle, and then at the end we will come to the your igniters. Now nozzle, here we use lot many different kinds of nozzle, in particularly for an solid rocket motors. Okay, so these are the possible nozzles are used. One is a fixed nozzle. Second is movable nozzle, like if you have a gimbal mechanism, right? Movable nozzle is submerged nozzle. Submerged means it will be hidden, the nozzle will be hidden. Opposite of submerged, extendable. Sorry, you can extend this particular length of the nozzle or the cross section. Okay, so these are the possible types of nozzle. Okay, clear? Shall I move to the next? Shall I? Okay, next comes injectors. Okay, so injectors basically have two different types of injectors. Okay, one is the bailed basket injector. Second one is an pyrogen injector. Okay, or this is also called as a pyrotechnic. Okay, pyrotechnic and the pyrogen. Okay, so pyrotechnic or bailed basket injectors, igniters, and another one is a pyrogen. Okay, so these are the two types. Next comes how this ignition process occurs. Okay, shall I rub this part? This they are like based on the process, okay, the mechanisms. So if I want to say, if I want to use for a small rocket motors, okay, that time I can use I can say I'll be using pyrogen. Okay, so if for the large like first is they have the different operation process are different. Okay, second difference is where it will be suitable, uh, like which kind of pyrotechnic will be suitable or the pyrogen will be suitable. Okay, because it also having different types of casings are there. One is a cartilage loaded grain, another is a case bonded grain. Okay, so based on this particular type, this ignition or the igniters will be different. Okay, so again the solid motors can be classified in two different types. One is a cartilage loaded grain, another is a case bonding. In the case bonding, if you can see, sorry, if you can see here in case bonding, it while manufacturing this your solid rocket motors, it will be built at spot. Okay, got my point? It will be in it will be like there will be no separate assembling of this propellants and then feeding into it. Okay, both will be compiled. But in case of cartilage loaded grain, it will be like assembling one by one, one after one, right? So that's a main difference between these two solid propellants. Okay, so that these two different types will differ you the different usage of this pyrotechnics and the pyrogens. Clear? And as I've said, pyrogen will be used for mostly small rockets, and it does it because small rockets means it doesn't can produce as high energy as compared with an you can it can be used for the pyrotechnic igniters. Okay, clear? Clear now? You can just unmute and let me know. Is it clear? Okay. Okay, next comes that how this ignition process occurs. Okay, we don't need to remember the all the things, but only the flow chart I will say. Okay, how this ignition process occurs. Okay, how? Because they don't ask much of the thing, maybe they can ask the sequence of the ignition process occurs for an solid rocket propellant. Okay, solid rocket motors, so you should know the steps how it includes. So for any injectors, right, any injectors, first they receive a signal. Okay, first they receive a signal, right? So after they get an electric signal, it will get spark, it will get heated up. So heat generation will occur. Once it get a signal, it will get ignite. It will like it will get heat generation over the surface. Then from there, what will happen? This particular heat will transfer into the grain surface. Okay, this heat will transfer to grain surface. Once the heat started to grain surface, it will the flame the particular surface is start to burn. So once it start to burn, it is like agarbatti. Once it started to ignite, you cannot stop. It has to completely fulfill the burning process. Okay, so once it get ignite the surface, right, then next will be your flame over the grains. I can say there will be a flame over the grains and it will start it to burn, right? Clear? Right? Please let me know if it is clear. Clear now? Okay. Okay. See, okay. Good question. See, for in case of liquid propellant, okay, for liquid propellant we have a separate tank called fuel and the oxidizer, okay. So based on our requirement, we can whenever we are feeding it, the combustion process will go on, and it will be gone, right? But in case of solid rocket motors, okay, once it started to ignite, okay, once it starts to get ignite, we cannot stop, because just see this particular diagram, okay. So just consider this is a igniter, okay, this is a igniter I have. So from it received the signal, it will started to generate heat, right? Heat will dissipate across the cross section of the grains, right? So grain surface will get heated up, right? Once it get heated up, it will decompose gradually, right? So across the surface it will decoy, and finally it will go. There is no mechanism. It is like one surface will get heated up means another surface will be automatically get burned, like how the process you can see in agarbatti, right? So there is no process that we can stop it, okay. You got my point? Okay. So no, nothing is there, because see, this is the igniter is there, if the heat is generated, it is dissipating to the nearing grains, like gradually it will decoy, and it will go expel out, right? It will expel out from here. There is no way that we can stop. That is a thing for an solid rocket motors. There is no that we can spray something or we can to stop. So that is for solid propellant. Once it start to ignite, it will, like, we cannot stop it, okay. Yeah, liquid, yeah, liquid we can control, but here we cannot control at all, okay. And ignition, first we are receiving the signal, right? First we are receiving the signal ki somebody have initiated ki now we should ignite. Now once it receives the signal, it will generate heat. So that heat will be liberating outside, right? And this heat will be transferring to the grains. So this grain, once it receive the heat, it will started to get a flame, and it will started to, like, decompose or started to get flames, okay. That started to burn out, I can say, okay. Now this burning having another three different types, okay. This burning process have three different types. So okay, three different types. So first one is like progressive, then neutral, then the recessive, okay. So this defines that. First I will start with the neutral one. Neutral explains that neutral explains that the that motor, when it gets burned, right? So it will have its own constant thrust, pressure, and burning surface will be constant throughout the burning process time. Is that clear? Like, whatever the fact, that is thrust, pressure, and the burning surface area, that is, if this is the propellant, right, is the igniter, if this is a propellant we have, so how much amount of burning, like, it should be constant. If particular time period, for an example, you have 120 second, the 120 second it will be burn equally, right? It will be not like half surface here more burned, here less burned, right? So as the time goes, the process of burning will be quite steady with its pressure, right? You can see, you can understand from this particular graph. Clear? That means the thrust or the pressure or the burning surface will remain same at a process of burning time. Clear? Then comes a progressive. Progressive means, as you can see, as the burning time increases, right, burning time increases, your pressure thrust is also gradually increasing, right, also gradually increasing. Then recessive means, you can understand, as it started to ignite, right, as we increasing the burning time, the pressure thrust is decreasing, and this regressive and the progressive and the neutral, all those things depends on the different types of grain sizing. What should be, which grain sizing will give the which progressive or the regressive one. Okay, so here you can see a few of the example, right? So if I consider the first one, see, burning, every propellant will be having its own burning time. Okay, how much, suppose if you are using thick agarbatti and one is a small agarbatti, right, so both the burning time will be different, right? And if you change the shape, right, if you change the shape of that propellant, their burning time will also be different. But the thing is, here we are talking about whether the burning is neutral, whether the burning is progressive or the burning is an regressive. Okay, so that defines that the shape, or I can say the grain configuration, that defines based on the grain configuration. So here we have the 6 different grain configuration, you can see, right? So among this, which one you can find the most effective one? Which among this you can find the most effective one? First one, we want a, always we want a constant, like if progressive also we don't want it. Okay, so though the thrust and pressure is, you cannot make more pressure, right, you, that is also not so advantageous. So always you have to look for the neutral one. More thrust, but you have to, if the pressure is more, then it can also burst your solid propellant can burst, it cannot resist that much of thing, right? So high amount of pressure is also not suitable all the time. Okay, it will be the second one, where you will can see it is a very much flat, that means it defines a neutral burning, right? The 1 and 3 you can see it is also almost like kind of progressive, it gets ups and downs, and 4 5 6 you can see it is for the regressive, right? Hmm? Yes, most of the thing used are, and they optimize the other parameters, right? This is in general. Okay, and nowadays they are optimizing the parameters. I hope you know what is meant by optimizing, right? So they optimize the parameters, and they do use that particular thing. Okay, so so we can find out the what is a burn rate. Okay, they have the following parameters that the burn rate depends on. So let's come to the point that what we need here is how to find out the burn rate. This is the formula to find out the burn rate. It is R dot equals to A. PC is the combustion chamber pressure, right? And N represents the burning rate index, or you can say combustion index. Okay, A represent is a Valley's law constant. Okay, Valley laws constant. Are you noting down? This is a very important formula. Okay, R is a burning rate or burn rate, which usually unit comes millimeter per second. Okay, millimeter per second. P is the chamber pressure, thrust chamber. Okay, unit is given over here. N is a burning rate or the combustion index, which is independent of the initial grain temperature, and describe the effect of pressure, chamber pressure, right? A represents the Rayleigh law constant. Okay, now we will solve one small problem based on the solid motors. Before that, these are the formulas. Please note it down, this formula. Okay, please note down this formula. This will be helpful for you to solve the problem. Have you noted the previous formula? Please note down this previous formula also. So they will be asking such small problems based on this particular formula. Okay, suppose in that case they have not given the A value, right? So you can find out the A value using this formula. Okay, this is a capital A. I just missed out. Okay, just give me a second. You note down the formula. Let me look into it. Okay. Given they have not given that. Instead they have given one more formula here. M dot equals to AB R into rho B. Okay, there is another formula has been given where AB equals to pi dB into L. Okay, you leave this part. Okay, mostly this A is given in the question, so you can leave that part. Or sometimes A is also known as a temperature coefficient or empirical constant. Okay, please note down, A is also known as empirical constant or temperature coefficient. Okay, N is also known as burning rate exponent or combustion index. Next important point, this R dot usually ranges from 3 to 4. Okay, okay, sorry, for this N factor 3 to 4 and this factor 0.05 mm per second to 75 mm per second. Okay, note down, this is another important point. When the N factor is 3 to 4, then R dot will be ranges from 0.05 millimeter per second to 75 millimeter per second. Okay, okay, Shall I move to the next formula? Have you noted down? Just note down these formulas. This is a very important formula. Okay, so this one represents that chamber pressure can be expressed as a function of area ratio of the burning surface to the A star means nozzle throat cross section, okay, for the given propellant. Clear? Have you noted down? Okay. Which one? AB. It is this is a burning surface. Area of a burning surface. Propellant burning surface, I can say. Rho P, this one? Okay, density of a propellant. Which one? This one? AB. They have not mentioned here, so just leave. Maybe, but we are not sure because it has been not given over here. So let's avoid that. Okay. Okay. Which one? This one? PC power 1 minus n. This one? This one? Okay. 1 by 1 minus n. See, you have to remember these formulas because you can expect a problem based on these formulas. Okay. And one more thing, remember the flame or any combustion temperature. Okay, because combustion temperature is an thermochemical property. Okay, so which will only depends on combustion pressure, which will not affect with an neither the exhaust velocity nor the flame radiation materials, anything. Okay, so that will only depends on chamber pressure, that you have seen how it depends on, right? It will only depends on chamber pressure. Which one? C star here? Characteristic velocity. Characteristic velocity. Okay, done? Done, right? Okay. Others, just let me know. Okay. Okay. So we can solve one problem, right? So this is the problem. A solid propellant rocket has an following data. Combustion chamber temperature has been given, combustion chamber pressure has been given, propellant density, grain diameter has been given, exhaust gas constant has been given, gas specific heat ratio, then Welly's loss constant is given, N is given, that is a combustion index given, burning time has been given, and the exit pressure. So from here what you need to find: the nozzle throat diameter, characteristic velocity, optimal thrust coefficient, thrust force, mass flow rate, and the total burn mass of the propellant, specific impulse, and the total impulse. Okay. So from this following question they can ask you the various kind of thing. Okay. So you have to use the previous, some of the previous formula which you have already used previously. Okay. Now can you how to find out this particular first one? To find out the first one, which formula will you use? That means you need to find AT or A star, right? You need to find AT or A star. Yes, please. Yes, just now we have seen AB by A star formula, right? Which one? A? Okay, okay, sorry, I just reversed that. Sorry, it's just, it will be A, okay? It will be A. Sorry. Just please note, make a note. Thank you so much. Right? This will be A. Right? A value. Welly's law constant should be 3 to 4. Okay? That's good. Okay. Okay. Now you have to use this formula, that is AB by A star. What was the formula? This is the formula, AB by A star. Okay? You remember this formula? You have noted down? So I hope all the values are given over here. This is the TC value, this is PC value, this is rho P value, right? What is this value? Which value it will be? D R A N. So instead of here the gamma value has been given 1.2 TB PE. So A value is also given, N value is given, right? So substitute in the formula, that is P C 1 minus N by rho P into A. We have gamma by RTC 2 gamma plus 1, gamma plus 1 by gamma minus 1, right? This was the formula. So using this you can find this AB value. Tell me, what is a nozzle throat diameter? Are you solving? Students, are you solving? Can just okay, fine. Please try to solve using this gate calculator already I have said. Tell me the answer. Give me the answer in 2 decimal places. Okay? Give me the answer in 2 decimal place in meter square. Acha, one more thing. Here you no need to convert the megapascal to the pascal. Okay? Keep it as it is. Because previously, you see here they have explained to keep that in megapascal itself. Then only it will satisfy this particular unit. Okay? You got it? Huh. Yeah. Yes. 4 point minus 3. That is the area you are talking about? Is the area? A star, no. No, 10 power, you don't need to consider 10 power 6. You have to take 18. Here you have to take 18. No need to keep 18 into 10 power 6 power uh, 0.4. No need to consider that. You have to just take 18 power 0.4. Okay? Please keep that in mind in case of rocket propellant. Okay? Rocket propellant, this is the formula belongs to likewise. Okay, so this is only when you are finding this burning and grain things. Tell me the value we are getting in 2 decimal place. Point 44. Are you getting the same answer? All of you getting the same answer? I have a different answer with me. Others, please tell me what you are having answer. Okay, so one thing we can do, I will just note down, give you the formulas, you can work out in your home. Okay, please copy the question, right? You can work out this kind of problems. So for characteristic velocity, this is a formula will be used. Please note down this formula. A star, I'm getting 0.12. Okay, so please note down this question, given data and the things formulas. Okay, this is the first formula, then C star, this is the formula. Thrust coefficient, you have to use this formula. Yes, we have AB is given, AB is given now. See, DB is given, so from DB we can find AB, right? Nobody is getting the same answer. So this is a formula for thrust coefficient. Anyways, you just try to recalculate once again. Okay, thrust formula is already known. What is the thrust? Mass flow rate is also, you know, that mass of total burn, you will get M means M dot. First you find M dot, then you multiply the time of burn, you will get that. Then mass flow rate, let me write this formula. Okay, this is a formula. Where? Which one? CF equals to 2 gamma square. Yes, 2 gamma square by gamma minus 1 into 2 by gamma plus 1 power gamma plus 1 by gamma minus 1. Okay, power, and it is whole root into, open the bracket, 1 minus PE, that is exit pressure, by chamber pressure, power gamma minus 1 by gamma. .24. Which value? Okay, Okay, let me recheck. I got 0.12. 0.2, maybe that because of the fractions change. Okay, but still nearing answer. Okay. Yes. Huh. Okay. So can I move to the next? Okay. So we will have another hybrid rocket. Hybrid rocket is nothing as simple as that. Here we will have the combination of that liquid oxidizer and the solid fuel. Okay, so instead of that, what will happen, in the injectors will be there. From the injectors, the solid oxidizer will be coming and spraying over here, so that will make it to get a combust. Okay, so here it is a combination of the liquid and the solid one. So solid will be the fuel and the liquid will be the oxidizer. Okay, so nuclear propellant rocket system is also there. One is a fission, one is a fusion. So mostly we don't use like nuclear propellant. So we have a small reactor. Okay, from the reactor that the propellants will be feeding into this nuclear propellant. It will get combusted. The same principle that you can have seen in the liquid propulsion. Okay, the instead of that, in the combustor, in the thrust chamber, we'll have some reactors. Okay, like how we have the nuclear power station, same likewise we'll have the nuclear reactors to undergo the fission reactions. Now that is, nuclear is not that important, but yes, but electrical propulsion is a bit important. They might ask you what is the specific impulse, they might ask you the comparative data of that specific impulse of those different types of electrical propulsion. Okay, so basically it having a different three types. One is the electrothermal, electrostatic and electromagnetic. Okay, so by the name you can understand electrothermal means what. We'll have some kind of so it having some kind of lot many different types of electrothermal. So you should know what are the types of electrothermal, what are the types of electrostatic, and what are the types of electromagnetic. Okay, so when I talk about electrothermal, the base example is an resistor jet, another one is a arc jet. Okay, so what will happen, by the name called thermal, right? So they will have some kind of wall, right? From they will have two different charge particles of the wall. So what will happen, due to this difference of the charge particle, and an iron gas will be formed. So it will get heated up, it will get ionized and it will expel out. So that's how the propulsion system will work in this electrothermal process. So that is the both the resistor jet and the arc jet. Electrostatic is like mostly based on the Hall effect or the ion propulsion. Okay, and electromagnetic means it will be having a pulse jet, or I can say the we'll have both the electromagnetic and the pressure forces. For an example, magnetoplasmic thrusters. Okay, the example. So this is the example for an this is an ion arc jet. Okay, this is an example for an arc jet. Okay, then this one is the ion. So we don't need the how it works much of it, but you should know like what are the types of like under which classification it comes on. Okay, that is more important. Second important is you should know the comparative study of all those different types, how which one is more which one is having the better specific impulse, and what are the possible propellants are used. Okay, so these are the main basic things of this electrical propulsion system. So from this, these are the types I've said. The registrojet, which comes under electrothermal. Arc jet also comes under thermal. Ion contact, ion bombardment comes under your electrostatic. And solid pulse plasma, MPD, arc jet, Hall effect, and monopropellant rocket. These are comes under the your pulse, and MPD comes under, MPD defines a magnetoplasma dynamic. Okay, magnetoplasma dynamic, it comes under the electromagnetic. So you can frame from this particular thing which one is having the highest specific impulse. So which one is having the highest specific impulse among all those things? Which one is having the highest specific impulse? Which one? MPD, arc jet, right? And which is having the least among all those things? Which is having the least? Monopropellant. Then after to monopropellant, we will having the, we are having next is, we having arc jet. Arc jet. After arc jet, we have the solid pulsed plasma. Then ion and Hall effect remains almost the same. Then the highest peakest is the MPD, that is a magnetoplasma dynamic. Arc jet is having the maximum specific impulse. So you should know which among this is an highest specific impulse. Next, you should remember what are the possible propellants are used. So in case of your electrothermal, so we use, these are the possible propellants. Okay, so N2H4 means what is, what we called N2H4, what it defines, what does it mean? N2H4, what is its name? What is N2H4? Hydrogen, right? Very good. So mostly we use ammonia, hydrogen, nitrogen, hydrogen. These are the possible things we use in electromagnetic. Okay, now looking into the ion propulsion, okay, ion bombardment, we use mostly argon. Okay, argon, that is AR. Okay, then in Hall effect MPD, we use argon, hydrogen, right? Xeon is also used, right? So you should remember these things. Okay, now next important thing you will need to remember what it efficiency represents. Efficiency of any this electrical propulsion represent that power output, power thrust power output by the electrical power input, because here it is an electrical propulsion, so we will be using the electrical power output. Okay. Next comparative data is this. This is a combination of both the chemical, liquid monopropellant, your electro thermal, then static and magnetic. Okay. Now among this, which one provides the maximum specific impulse? Which one provides the maximum specific impulse? So if you have the comparative thing, So remember the electrostatic, whatever the electrostatic means, either it is a Hall thruster or the iron thruster, will provide the maximum specific impulse. Clear? Right? Hall thruster or your iron thruster. If you have iron, then iron will go to first priority, then comes the Hall. Right? Next will be your electromagnetic. Next will be having plasma or the electromagnetic. Okay, electromagnetic thrusters. Right? Second will be your electromagnetic thrusters. Then second is electromagnetic. Third will be your electrothermal thrusters. Okay, clear? Are you noting down the points? Third will be your electrothermal, the second highest, right? Then followed with solar heating. Okay, then followed with a solar heating or the cell rocket propellant. Okay, propeller. Then we'll be having our chemical. Among this chemical, the liquid propellant will be having the next priority, then followed with the solid, then comes the hybrid, and at the end we will have the liquid monopropellant. This is the sequence it will follow for a specific impulse. Clear? Is that clear? So you have to identify among that. Okay, so first one comes your iron, electrostatic. Among the electrostatic, iron will be coming the first priority, then comes the Hall effect, right? Then will comes the electromagnetic, then electrostatic, right? Then after electrostatic we'll be having the solar cell rocket, right? Then will come the chemical. Among the chemical, which one will be that? First will be the cryogenic, then liquid, then we'll have the solid, then hybrid, right? Then we'll have the monopropellant liquid. This will be the sequence. So you have to identify and choose the answer accordingly, right? Clear? Okay, so that's all. We have completed the propulsion, right? So if you have any other questions, please let me know. So we have completed the propulsion syllabus. So always remember the tables and the graph which I have discussed. So please to remember the tricks I have used for remembering the formulas for in case of turbo machineries, right? There's all those formulas you have to remember.